Thanks. My name is Justin. I work at Google, and I work on the Polymer project, who's been involved with web components for a long time now. And right now, we're going to talk about building complex applications with web components and LitElement. And the first thing I want to do is get my clicker working. OK. The first thing I want to do is tell you to hold on. I want to give a little warning because this is going to be a whirlwind of a talk. Complex applications is just far too big of a topic to cover in any depth in a day, let alone a single talk. So I'm going to go really fast and touch on just a few key points. But first, I wanted to start with telling you why I wanted to give this talk, why I think it's such an interesting topic. First is because a lot of developers ask us questions about this. It's sometimes easy to focus on how to build individual components and maybe scale that up to a few components that collaborate together. But the story just gets so much more complex when you try to scale that to a complete application. And the Polymer team has talked about this a bunch. We've given a lot of talks at conferences, written documentation, and we've even built products around this like PWA Starter Kit to help developers get going with full applications. And we have a lot of people out there building complete applications with web components, top to bottom, meaning no traditional framework, and the app itself is a web component. Apps like YouTube, that's probably the most well-known example. And they have a bunch of apps like YouTube Music and Creator Studio and all their internal apps as well. Other Google apps like Google Play Music, Google Patent Search, these are built with web components top to bottom. And then non-Google apps, we have things like e-commerce sites like 1-800-Flowers. This is web components top to bottom, and it's actually the first PWA that was published to the Google Play Store alongside of Android apps. And this app actually outperforms their previous native Android app, and it's all web components. ING is going all in on LitElement and using it to deploy their applications across all their markets around the world for their consumers. And now we're starting to see interesting complex creation apps. Chrome OS is developing a drawing app, and we know about apps in the pipeline that would traditionally be complex desktop applications that are coming to the web with web components. So this is going to be a very fast talk, and instead of going very deep into one type of feature or explain how a specific app was built, I wanted to try to get into the underlying techniques and patterns that you can use to address a number of the challenges that applications face. So throughout this talk, I'm going to be showing examples and example code, but the point isn't to focus on that one single implementation. Most of it is purely demo, and it's not really published anywhere. But I want to show off these techniques in real code, so that's what the samples are for. And so hopefully you can see these common patterns at work and maybe apply them to your own applications at some point. So let's start off with some terminology and concepts. I know not everyone here is familiar with web components, so I want to define some things so we all get on the same page. Let's start with applications. So what is an application? What makes it different from a component? Like maybe an application is just a very large component. It has data, but it's complex data. It has subcomponents, but a lot of them. And this is true to some extent, but applications have unique concerns that components generally don't have. Things like routing, UI singletons, which might be like the app shell, or maybe an overlay system if you're going to display modal dialogues or progress indicators. You might have generic services like logging handlers or error handlers that you want to use across a whole app. You might have global state, like the currently logged in user. Or maybe you have a scheduler so that long-running tasks don't jank the page. So these are things that are generally unique to applications. And so if we think about an application as a collection of components, you might draw a diagram like this, some hierarchy of components. And what a lot of people think differentiates an application is that you have this orchestrator layer sitting on top of your component hierarchy. And this orchestrator owns a couple of services, or many services sometimes. And these services are going to be distributed throughout the app, and components are going to need to access them no matter where they are in the component tree. So this is kind of a visualization of what makes applications different from components. Next, let's do a fool's errand and try to define frameworks. There's a lot of different definitions for frameworks out there. I'm kind of particular to this one that says frameworks define the component model, but that's not really helpful today. A good definition for today is that a framework is the application scaffolding and glue. It gives structure to your projects so that when you start off, you're not starting from a blank slate, and you know where to fill in some holes to get your application going right away. So this is going to help us today because we can look at the types of things that an application offers, and we can think about how to do these things in web components just without the framework. So we have a list here, and this isn't nearly everything. This is just a sampling. All right, and then let's get into what web components are. It seems like every web components talk has to have this introductory thing, but I don't have a lot of time, so I'm going to give the briefest of overviews of web components. The easiest way to explain them is that web components are the native component model of the web platform. So the web platform has evolved into an application platform now, and pretty much every single application platform out there has its own native component model, and so the web should too. There are a number of different features for the web platform that come together to form web components, but the two most important are custom elements and shadow DOM. So custom elements briefly let you define new HTML tags. The browser is no longer the sole arbiter of what tags actually do something on the web page. And then shadow DOM gives us DOM and style encapsulation, and it also gives us composition. So to see what web components look like in use, imagine you have a static HTML page here, and you want to throw an image carousel in the middle of this page. Now, the browser doesn't have an image carousel built into it, but we can go out and find one, and as long as we import the definition of this image carousel, then we can go and use the carousel just like any other HTML tag. And when we go to load the page, we're going to render this carousel, and the images are going to be inside of it. And we're very happy because this worked, and it's just a simple HTML tag. Another thing to note here, though, is that the carousel actually has some of its own UI. These are not tags that we put in the main page, and neither did the carousel put these tags in the main page. It puts this UI here inside of its own shadow root, and it's kind of hidden away and kept safe from the rest of the page and the rest of the styles. To look really quickly at what it might be like to implement a web component, there are three main things that we kind of have to be concerned about. So the first is that we need to define a class. Custom elements are class-based, and they extend HTML element. So this isn't like a component model where a component owns an element. This component is an element. You're actually extending the vocabulary of HTML. Once you extend HTML element, you need to tell the browser about your class. So you do this by calling custom elements.define with a tag name. And now when the browser sees this tag name, it knows it needs to create an instance of your element. And then lastly, we have a set of lifecycle callbacks. So these are methods that the browser calls for you when certain things happen with the element. When you get a new element, it's going to call the constructor. When you attach to the document, it's going to call connected callback and so forth. So this is where you put the meat of your implementation for a web component in these callbacks. Okay, and then really quickly, shadow DOM. So shadow DOM is kind of like a document fragment that is still rendered to the page, and it's your own private kind of place to put DOM for the component. And the API for doing this in the browser is an imperative API called attach shadow. So you call this, and you get back a shadow root that is attached to your component. And then you can populate that however you want. You can use a template library. You could use Preact or LitHTML. You could clone an HTML template. In this case, I'm just showing the simplest possible thing, which is just to use inner HTML here to put some tags there. So that's web components in brief. They give a few new capabilities to the platform. You can define new HTML tags. You get encapsulation. You get composition. And you get this lifecycle. And that brings us to LitElement. LitElement is all about helping you implement web components. It's a base class that you extend, and it provides a useful API for building the components. And it should mostly be an implementation detail of your component. Users of the component shouldn't really have to know or care that it was built with LitElement. So this is what a very simple LitElement looks like. This is the typical hello world example. And I'm going to note real quick that I'm using a little bit of TypeScript throughout the samples in this code here. And I'm doing that because I'm super fond of decorators. And I really hope decorators come to the JavaScript language. But I really think that they make APIs more declarative and easier to read. So I'm going to use these throughout the samples to make them shorter. And I hope it's not confusing that I'm using a feature that doesn't quite exist in JavaScript yet. Okay, so LitElement gives you a few things here. First, we have the custom element decorator, which is very simple. It just registers the element with the browser. Then instead of extending HTML element, you're going to extend LitElement. Now, LitElement itself extends HTML element, so this is still a web component, and you have access to all the standard web component APIs. Next, we see here that we have a declarative styles block. So LitElement takes care of pulling in these styles and applying them to the shadow root in the most efficient way for whatever browser you're running on. Next up, we have declarative reactive properties. So this decorator here, when applied to a class field, replaces the field with a getter and setter pair for your class. And what this allows us to do is to react to changes when that setter is called. So when something updates the property on this component, it's going to recognize that and then cause the component to be re-rendered. And lastly, we have a render method. So this is a method that you implement and then LitElement calls when it needs to. And this method simply returns a little bit of LitHTML. Now, I don't have enough time to go into LitHTML in this talk, but it's a template library that we maintain. And the easiest way to think about it is that it's a little bit like JSX, just with standard JavaScript syntax. So it uses these tag template literals, and it focuses on the HTML in the string parts of these literals. Everything in the expressions is just standard JavaScript. So it's very much like JSX that way. And it doesn't have any control flow constructs of its own. So if you need to do conditionals or looping, you have to do that with JavaScript. So it's like JSX, but it does happen to be one of the smallest and fastest view libraries currently out there right now. OK, so that's Hello World LitElement. Another thing besides this declarative interface that LitElement gives you is the LitElement update lifecycle. So LitElement always renders asynchronously. And the way that works is that anything that's going to cause the state to change for an element that might make it render differently is going to flow through this method called requestUpdate. So if you set a property or set an attribute, connect to the document, it's going to defer most of its work until later by calling requestUpdate, which is going to enqueue an update task on the browser's microtask queue. And so this gives us this async batching boundary. So if we set a bunch of properties in a row, we're not going to get a bunch of renders in a row. They're all going to kind of coalesce into a single render task. And when that task runs, what it's going to do is going to call the update method that is implemented by LitElement. And that update method is going to call your render method, get the LitHTML template back out of it, and apply that to your shadow root. And we do this for a couple of reasons. So one of them is for performance. So if you set a bunch of properties in a row, you're not going to get a bunch of renders. You just get one render. That's good for performance. And another is because it makes it a little bit easier to reason about your templates. If you have a whole bunch of related properties, you can kind of expect that they're going to be set together, and you're not going to have to render all of the intermediate states and think about those in your template. So the main features, again, that LitElement gives you is declarative rendering, declarative reactive properties, and this async update lifecycle. Everything else that you might need to do is left up to standard web components and standard JavaScript. So LitElement is really trying to be this thinnest possible layer on top of web components. So if we go back to our partial list of features that a framework might give us, and we look at what we get just from web components and LitElement, we actually start ticking off a few of these here. We get components, we get templating, and some amount of reactivity. And so that brings us up to the rest of the things. And I don't have nearly enough time to get into them, so I'm going to pick 5 of them right now to get into. We're going to cover routing, code loading, asynchronous tasks, dependency injection, and state management in just the short amount of time I have left. But let's start off with the application. So an application is just going to be a component. And there's actually 2 main ways that you can structure the kind of an application at the top level with web components. One way is to have the page itself kind of be the application. And you sprinkle a bunch of components around in the page that implement the dynamic parts of your page. And they might communicate with each other somehow by finding each other through events or JavaScript. But you actually have kind of a static web page in a sense that turns into a dynamic application. And there's a lot to like about this pattern. But the other pattern is that you just have a single root element that basically implements the entire page. And I'm actually going to go with this method today because it makes it a little bit easier to take advantage of JavaScript features so we can move a little faster. So if we go back to our diagram of what an application is compared to a set, just a set of components, what we're going to try to do here is remove this orchestrator and fold some of the logic that it has either into the app or decouple it completely so that components can collaborate without an orchestrator at all. And so that brings us to the first feature that applications usually need to implement, which is routing. So routing is basically determining what views and data to show based on the Windows location, based on the URL. And so we're going to tackle this, and in doing so, we're going to cover some patterns here. We're going to use coordination between components with events. We're going to look at unidirectional data flow and decoupling things via data and events. And to keep myself honest here, I wanted to make sure that my demo code actually works, so I built a sample application, and it's a little email application. I'm not going to run it, but I have some screenshots. And it's relatively simple. It has two views, an inbox view and a thread view. And for routing, we're just going to want to switch between these. And the first recommendation I have for doing this is that rather than driving your routing from URLs, think about it as you're using the data to show the different views. And I'll show you what I mean by that here. So the first thing we need to do if we're going to show a couple of different views is actually have some views to show. So we're going to go ahead and import two components here that represent our views, the inbox view and the thread view. And after we import them, we can use these components in our template. In order to drive this by state, we're going to introduce a new field into our application class here called current view. And this is a string that can take one of two values, inbox or thread. And then we're going to write a little helper here called render current view. And this is going to switch on the current view, and depending on if it's inbox or thread, we're going to show an inbox component or a thread component. Pretty straightforward. And then finally, in our render method, we're going to assume that we have some app scaffolding. Here I'm using the material design drawer as kind of the app shell. And it has a slot for the main app content, and we're just going to call our helper right there. And so this alone gives us the ability to switch views just by changing this current view property here. And so now we have something that's kind of routable, but not by URL, it's by data. So what we're going to do after this is we're going to plug a router in to parse the URL and set the data. You can use any router. The one I'm going to use right now is page.js. I like it because it's super small, it's 1K. It has an extremely simple API, and it's published as JavaScript modules to NPM, so we can build this demo without a lot of tooling. So to use it, first we have to import page. So we can use this page API here. And then next, what we're going to do in our application component is in the constructor, we are going to call the PageJS APIs to define some routes. These are very specific to PageJS, so I don't want to go into too much detail there, but basically you define some URL patterns and some callbacks to call if the current URL matches those patterns. And we're going to define two such callbacks here, the inbox route callback and the thread route callback. And they're relatively simple, because all they have to do is set the current view to the appropriate value. In this case, we're going to set it to inbox. And then they pull some of the data that was parsed by the router, and then pass that data on to an API that's going to fetch the content that we need to show. So it's a fairly simple routing setup. And if you're driving your routing from data, you might call this data-driven routing. And the idea behind it here is that what to show is driven by data, and the router is only responsible for parsing the URL and producing new data, and the components end up being very decoupled from your router, which is a good thing to do. And we can kind of visualize this here by seeing that if we have two different URLs that feed into our application, they're going to hit the router, get parsed, create new data, and that's going to flow down through the page. All right, but that's not all you need to do if you're doing routing. You can't just take a URL and show something. A lot of times you have to have some actions that change that URL. So let's look at how we'll change routes. The first way is just to use an anchor tag. If you have all the pieces of data that you need to construct a URL and you know what the form of those URLs is, it's very easy to just create an anchor tag and use some interpolation to put the right URL there. And then the router will listen for the click events, and if it sees that a click event came from an anchor tag, it will invoke the routing logic, and off you go. So this is great for accessibility because the accessibility readers and crawlers are able to see the anchor tags and know that that's a link. But sometimes you might want to do something a little more dynamic, so we're going to look at changing routes with events. And the idea here is that instead of directly changing the route, we fire a semantic event from a component that's doing a navigation. So this might be an event maybe named like show thread in our email example. And then the application is going to handle these semantic events and update the route. The router is going to handle the route change, create some new data, and then that data is going to cause our view to change. So that's what this looks like here. In our application, we're going to have an event listener for this show thread event. We're going to grab some detail off of this event, like the thread ID, and then we're going to call our router API to change the route. And in the thread component here, we're just going to fire a custom event called show thread. And the key part of this here is that the detail has the thread ID that we want to show. And so that gives us kind of this unidirectional data flow through our routes. This is going to start with some kind of event in our page. That's going to flow up to our application, which is going to change the route. That's going to hit the router, change the URL, cause there to be new data, and flow down through the page. And this is going to make it very easy to reason about the flow of data throughout route changes in your application. And that brings me to my next topic, which is code loading. So we had a very nice router set up. It was simple and decoupled. There was one problem with it, however, and that was that we eagerly imported the views. This might be fine to do if you only have 2 views, but as your app scales up in complexity, you're going to pay the cost of loading the implementation for all the views of your app, even though the user might only need to see one of the views. And this is going to make your users very unhappy. You're going to have large JavaScript bundle sizes and a slow app. So we're going to solve this, and we're going to look at using dynamic module loading and some LitHTML directives to do it. So the key point here is to avoid static imports wherever possible. Prefer dynamic imports. They're going to be better for code size. And we're going to use this to implement lazy loading components. So what we're going to do is we're going to build our own directive here that we call lazy load. And this is a very simple directive. It basically creates a place to put a dynamic import. And it takes a template, and it's just going to pass that template forward and render that template when the dynamic import is done. This implementation of the directive doesn't really do much, but I'll show it anyway because we're going to expand on it later. A LitHTML directive is a special kind of function that takes some parameters, and then it returns another function which gets a part. And a part is basically a reference into one of these dynamic locations inside of a LitHTML template, and the directive can directly set the value of that part. So here we're just going to wait for the promise to resolve and record some information that it resolved, and we're going to use that later. And then we're going to take the value, which is the template that we passed in, and we're going to set that to the part, which is going to render it. So we can go ahead and use that in our current view helper. And here, instead of just returning the template, we're going to return this directive. When we hit this case in the switch statement, it's going to cause this import to load. And now we're dynamically loading the components we need based on the route. So we can go back to the application component. We can look at our static imports. We know they're bad, and we can delete them. And now we've made our users happy. And hopefully this video works here. Oh boy, video cannot be loaded. We're going to skip this. It shows the routes happening and a little bit of delay happening because of the asynchronous loading of the modules. And if you could see that, you would see the motivation for the next topic, which is dealing with async tasks. So another differentiation between applications and components is that applications are more likely to have to deal with async data. And one of the things that happens with async data is, in that video, is you were going to see the UI paint in incrementally. And it's not really great to have UIs change underneath of a user without letting them know. So one principle we should stick to is that we should let users know when there's some async work pending. So we're going to tackle this one right now, and we're going to use a couple patterns again here, coordinating components together with events, and we're going to look at organizing code using JavaScript mix-ins. So here's another video that cannot be played, but this shows the UI coming in incrementally. And so instead of having the UI come in incrementally, what I want to do is show a progress bar at the top of the UI. And so luckily, we're using our material design component set, and we have this linear progress bar. This is just going to sit at the top of the page, and when there's some work happening, it's going to scan back and forth. So we have this component, and the only problem is that the component is controlled by this closed property here. When it's closed, we don't see it. When it's open, we see it, and it's moving back and forth. But we need some state to bind it to. We need to tell when it should be opened or closed. So how do we do this? Well, what we're going to do is use something that I call the pending state protocol. The way that this works is that when some component has some async work to do, it's going to fire an event called the pending state event. It's going to fire that when the work starts. And that event is going to carry with it a promise that's going to resolve when the work is finished. In this way, any containers above that component can listen for those events, and they can keep track of the number of outstanding promises so they know when there's any pending work left to do under those containers in the tree. So this means we can fill out this to-do section that we left here in the lazy load helper. And we're going to fill that in simply just by firing another custom event, this pending state event. And the key thing here is that this carries a promise, which is going to be the same promise from the dynamic import, and this is going to resolve when our module has loaded. And then we want a container that can respond to these events and kind of know when there's async work that is left to be done. And so we're going to use a Mixin pattern. What this is a function that takes a class and subclasses it. Now, this is kind of like any subclass that you would normally write with classes, except for you don't have to know the superclass ahead of time. You can actually extend any class. What's nice about Mixins is that the rest of the Mixin is just a normal class, so everything you know about a class applies. And in our case, it means that we can put class fields in there that are decorated with the LitElement property decorator so they become reactive. So we're going to have two properties here. One is has pending children. This is a Boolean that says if there's async work going on below here. And the other is the pending count, and this is going to be the total count of async tasks that are still outstanding. And this Mixin is relatively simple. We're going to add an event listener for these pending state events. So when we receive one of these events, we're going to set has pending children to true, increment our pending count, and then we're going to wait for that promise to complete. When it does, we're going to decrement the pending count, and if it goes back to 0, we're going to set has children to false. And because these are reactive properties here, when they change, it's going to cause the component to re-render. So now if we want to use this Mixin, the first thing we do is apply it. So this is a function that takes a class. We're going to pass it LitElement, and we get a new thing to subclass that has these properties on it. And then all we have to do is bind to this has pending children property. And whenever this property changes because the async tasks started or completed underneath, it's going to cause a re-render, and this is going to update. So now we get to see our progress indicator go whenever there's work going on below it. And you cannot see it. This is the last time I do videos in Google Slides. OK, so that's how we can get a top-level progress indicator that automatically shows up if there's any work happening anywhere in the app. And again, this is very decoupled via events. You can write any number of container implementations and helpers. You can write any number of task helpers that fire the events for you. And they can all work together if they work over this protocol. So I think this is a very promising area for collaboration between web component authors. I've published this description of the pending state protocol to GitHub, and I think there's room for a few more protocols like this. So hopefully we can get kind of an ecosystem going around these. So another thing about async data is that it's a little bit trickier to render than synchronous data. One part of that is just kind of re-rendering when data changes, and that's not too bad. But there's a lot of different ways that data can be async. Sometimes the asynchronicity is layered. You might have like an async API that just gets another async API that then gets you the data that you wanted. We see this with hosted APIs a lot. Or you may need to collate synchronous and asynchronous data during rendering. Let me give you one example of that. So in the email app, I wrapped up the Gmail API in this helper class that exposes these clean async functions to get data. And one of them is get labels, and this returns a promise of the user's set of labels. And this turns out to actually be a really important API in the email app because everywhere a label is used throughout the data model, it's only referenced by ID. If you want to get a hold of the label's name or the color, you have to look it up in this map, and this map is provided asynchronously. So if we were dealing with this in an async function, this would be pretty straightforward. We can just wait for the labels to show up, and then we could just synchronously iterate through them and write them out to the console. So we kind of want to do this in our component. A component should be a function from state to UI, after all, and so we can think about the properties of the component as the arguments to the function. And it would be really nice if we could just kind of await the labels showing up in our render method and then use them synchronously to get names for the label IDs. But we can't. So as much as LitElement's lifecycle is asynchronous, the render method itself is synchronous. We could possibly make it async, but we keep it sync for a couple of good reasons. And one of the big ones is that if it was async, it would be very easy to drop and await somewhere in your render method and then block your whole component from rendering because you're waiting for some data. And what we would rather have you do is render something that acknowledges that your component did get to go and maybe keep a placeholder there for the asynchronous data. So we don't want you to render nothing just because something is loading. So what we want to do here, instead of awaiting this inside the render method, is we want to try to treat the async data like it's synchronous. So we're going to tackle this again. We're going to look at some patterns like caching the async data, and we're going to look at how to hook up to the LitElement update lifecycle. So here's a component that represents email thread. And what we're going to do here is we're going to create a property that's going to hold the asynchronous data after the promise resolves, after we get the data. And we're going to override or implement this LitElement lifecycle callback called first updated. So this is called after your component first renders, and it's a good time to do one-time work. And we're going to call the asynchronous Gmail API and just stash that data into that property there. And when we set that property, the component's going to re-render, and now we can use the data like it's there synchronously. Yeah, so then in our template, we can just check to see if we have the labels. That'll be undefined before we run that method. And then if we do have the labels, we can just go ahead and access them synchronously. So that's pretty nice. It's pretty easy to follow, I think. But it doesn't necessarily scale that well. If you have a lot of different async operations that you need to keep track of, or if they're interdependent, things can kind of get messy in those lifecycle callbacks. So we're going to try to improve the developer experience here by creating a new helper that I'm going to call a cached task. And so when we tackle this, we're going to look at a couple other patterns. We're going to treat async tasks as values. These are first-class values that represent some work being done. And we're going to trigger the LitElement lifecycle with request update. And then we're going to look at some decorators. So the API for creating a cached task looks like this. We want to give it a host element that it's going to call request update on to trigger a new update. We're going to give it a task function to do the actual work, and then we're going to give it a get dependencies function. So if the dependencies of this task change, it'll rerun it. And we use it like this. So the host we give it is going to be the thread element itself. The task function is simply going to call this Gmail get labels API. And then the dependencies here, we're going to say that if for some reason the Gmail API instance changes, that we're going to want to get the labels again. And so I'm not going to show the implementation of a cached task because it just has a lot of bookkeeping around whether the resolve state has changed and things like that. But basically what it does on the inside is it treats a task as a value, and it's converting the async value to sync by basically waiting for it to resolve and then storing the value. And then when the value is ready, it invokes LitElement request update, which triggers the whole request lifecycle. And finally, it fires one of those pending state events, just like we did with the loading helper, so that any asynchronous work triggered by this cache can be dealt with by containers and included in progress indicators. And then finally, if the dependencies change, it's going to recompute the value. And once you have a task, the public API is very simple. It only has a value getter on it. So this is undefined before the task completes, and then sometime later, it's going to be defined to the value after the task completes. And we can use it like this. Inside of our element, we can create a class field that's going to have a value of one of these cached tasks. And then we can check to see if that task has a value or not. And if it doesn't, we'll render nothing. And if it does, we can just use it and get the values. So this is a little bit better, but it's still a little bit cumbersome. We have to access this value from this task object. So let's try to improve the developer experience a little bit more with a decorator. So what we're going to do here is we're going to try to avoid having to directly reference the task like this. That's just a little bit cumbersome. So we're going to create a decorator over a field. And the nice thing about decorators is that they can replace this field with an accessor. So we can hide the task behind a getter. So now the field is not called labels task, it's just called labels. And we can directly access it because the decorator is taking care of creating the task for us and wiring this through. And so now this looks more like regular synchronous data, even though it's an async task. So that's async tasks. The general idea with these things is that you should notify if there's pending work going on. You should try to convert async values to synchronous values so they're easy to deal with in rendering. And we try to create developer-friendly abstractions for them. And speaking of developer-friendly abstractions, Let's move on to dependency injection. So a lot of frameworks out there include dependency injection as kind of a core functionality. And what dependency injection really is a way to give components access to non-local data so they can get their hands on this faraway data. And the reason why you might want to do this is because in most data binding and data passing systems, you'll get your data from your parent component. But there might be some things that you want available all across the app, and you don't want to have to pass down from component to component every time. This is often helpful if there's cases where you're going to add a new component somewhere deep in your UI tree that needs data that you haven't previously wired there. So let's say you want to show the user's avatar somewhere deep in some navigation menu, and you haven't been wiring the current user down into that menu. You don't want to have to change the code for every component from this avatar all the way up to your application just because you need the current user. So with dependency injection, you can provide the current user to anybody who wants it without a direct reference from its parent. So the patterns we're going to look at here is coordination with events again, mix-ins again, and decorators again. So hopefully you can start to see how the common patterns can put together in different ways to solve different problems. So what kind of objects do we want to inject with dependency injection? This might be things like APIs, like that Gmail API. We might want to inject themes across the whole application. Common services like loggers or caches or other services that you can imagine that you want across your entire app. And dependency injection has some kind of typical requirements, right? Usually it relies on a central dependency injection container, or what's called an inversion of control container. And the idea here is that you don't construct objects yourself. You just ask for them, and the container actually calls the constructors. And then in frameworks, at least UI frameworks that have this, it's usually a tree-based DI, so you can actually have different dependencies in different parts of your UI tree. And even frameworks that don't have what they call dependency injection sometimes have something that accomplishes the same goals. So in React, we have the context API. And this is also lets you get at far-flung data, but it works a little bit differently, and it relies on having a shared API between the parent and the child that wants the data and everything in between. And instead of setting things in a constructor, the context APIs are usually available during render. But there's a little bit of tension here with custom elements. With custom elements, it's the browser that calls the constructor with no arguments. We don't have any control over this. And there's also no standard render callback. The render callback that you've seen here is an invention of LitElement. And we aren't able to rely on some common framework or API that the components share, especially if there's components that are far away from each other, and they might have some components in the middle that don't participate in this API. So to use this diagram again to illustrate our problem here, what we have is some component that wants to request some data, some component that wants to provide it. And so how are we going to get this between the components? We're going to go back to one of my favorite DOM APIs that I just used a few times, and we're going to do events again. And the way this works is that the requester is going to fire an event. It's going to bubble up the tree. It's going to be handled by this provider who's going to attach some data to it to make it available to the requester. And so now we're going to write another mix-in. We're actually going to write two, a requester and a provider. So the way the requester works is it's a mix-in that extends some base class, and it's only going to add one method called request instance. And this is just a little helper to make it easier to fire this event for us. So we're going to fire this request instance event, and we're going to make sure that it has the key that we want to request the instance by. This is probably going to be some kind of string that you use as an identifier for this object that you want. So then we dispatch the event, and events are synchronous. They fire up the tree synchronously, and that means by the time you hit the next line of code, if that event was handled by some ancestor and they attached an instance to it, it'll be ready for you to access here. So we can get dependencies synchronously just by calling this request instance method. The provider is also a mix-in. And so this is going to have the standard mix-in function pattern at the top. This is going to add a property to the class that stores the instances. This is going to be a map from the key to the actual instance. And then we're going to add an event listener for this request instance event. And inside here, we're going to get the key that we want off of the event. And if we have an instance that matches that key, Then we're going to set the instance on the event, and we're going to stop propagation so that other containers above in the tree don't have to answer this request. And then we're going to implement a provide instance method so that we make it easier for containers to set up the instances that they hold. So let's look at how we use these mixins. So here we're going to apply the provider mixin to the application component. And we're going to have some object that we want to share. This is going to be the email API itself. So we construct one of those. And then in our constructor here for the component, we're going to just say, let's provide an instance keyed off of this string mail API. And it's going to be this instance of the API here. And so that's all we have to do for our application. For the thread component, we apply the requester mixin. And now we want to fill in this property here, which is the mail API. And all we have to do is call this.request instance with the mail API key. And so that makes these two components collaborate across the tree with events. And we implement something very close to dependency injection. And we can even go further. We could make a decorator that we decorate a property with that collaborates with this mixin, and then it'll automatically request this component for you. So I tend to call this protocol here the dependency resolution protocol. So events give you the basic capability for components to communicate with each other. And then the mixins give you, wrap that up in a nicer developer experience. And then using this decorator here, we can even get to a better developer experience. Okay, and so now let's move on to state management. A lot of applications are built around state management frameworks as kind of like their core architecture. State management really takes state changes and it makes them centralized. And it tries to make them predictable by giving you a framework for how you apply state changes. And they typically enforce, or at least some of them enforce, unidirectional data flow. And one of the original kind of state management solutions is actually kind of available out of the box with web components. And that's this pattern of passing data down and events up. So we're going to take just a little look at that. And we're going to see we use some similar patterns again. We're going to do communication with events and try to enforce unidirectional data flow. And so the way that works in our component diagram here is that when we have new data, we're going to flow it down the tree via unidirectional data binding. And when we want to mutate that data, we're not going to mutate it directly, but we're going to fire some semantic event that's going to say something like maybe delete a record. And then the owner of that event is going to receive, or the owner of that data is going to receive that event, and it's going to do the actual data mutation. So that might look something like this. In some component somewhere, we're going to have some code to dispatch an event, and we're going to have a delete record event here, and it's going to contain some data to identify the record. And then somewhere in the application, assuming that's the thing that owns the data, we're going to handle this event, and then we're going to actually apply the mutation, in this case, deleting the record. And if you look at this, you might see some similarities to something like Redux. Events in this system look a little bit like actions. And the dispatch event method that's standard in the web platform looks a little bit like the dispatch on a store. So you can get pretty far just by using kind of the plain APIs that are available in the DOM before you even have to step up to a store API like Redux. But a lot of people do use Redux. And so I was interested in exploring how you could hook up Redux to web components. And it turns out a lot of people do this, and they have different takes on it. So I was trying to boil this down to the essentials and get across what principles apply to be able to hook up like a third-party data providing library to LitElement so that you trigger the lifecycle correctly. So we're going to look up handling these external updates. And again, we're going to use unidirectional data flow, and this time we're going to do composing mixins, which is an interesting technique. So first, let's look at how we want to use our Redux mixin. So what we want to do is basically imbue our component with the ability to get data from somewhere. And we don't even know where yet. This is just going to get it from some ambient Redux store. And then what we're going to do is something that's close to an idiomatic Redux pattern is we're going to implement this map state to props method here. So anybody using React Redux is probably familiar with this. And what this is going to do is just pick out the data that this component cares about from our store. And once we do that, we're able to have a very simple synchronous render method here. In this case, we care about our thread, and we care about the labels. And this Mixin is just going to put them into one variable called props. So now we can just access this.props.thread synchronously if it's there. And we can also get the labels synchronously if they're there as well. So this is fairly nice to use. Let's look at how we implement this. So the first thing to note is that this is a Mixin, but it's actually based on another Mixin. What we're going to do is compose the dependency injection requester Mixin here so that we can have the store injected into this component, and that the component that actually uses the connect Mixin here doesn't even have to be aware of that. So because we use this requester Mixin, we're going to have a request instance method on our component, and we're going to be able to request the store. After that, we just use the standard Redux APIs, and so we're going to subscribe to the store, which is going to give us a callback every time the state changes. And inside there, we're going to run the component's map state to props method on the state to get the state that we actually care about, the props we care about. And if those props are different from what they were the previous time, then what we're going to do is just call request update, and that's going to trigger the LitElement update lifecycle. And then to make sure we clean up after ourselves down here, if the component disconnects from the tree, we're going to unsubscribe from the store. So this is most of all that you're going to need to wire Redux into a web component. And you have these two different libraries that have two different concepts of how they schedule work to be done. And what we've done here is we've coupled them together by having the Redux scheduling lifecycle drive the LitElement lifecycle. So that's the state management part. We try to make sure that we do data down. It's very a good idea to decouple mutations by firing events up, or you can use Redux actions. And we've shown how we can hook external updates into request update to trigger the LitElement update lifecycle. And then we even combine it with dependency injection so we can get our stores automatically. So those are the 5 areas that I wanted to cover. And again, I wasn't so much concerned with the specific implementation of each one of these things. They all used some variations of some common patterns between them. And so there's a lot more than 5 different types of application features you might need to implement. But hopefully you can use these patterns, things like coordinating with events, lazy loading, treating async tasks as values, or plugging into the LitElement update lifecycle. You can use these patterns to implement other kind of large-scale and cross-cutting concerns that applications need. So I hope this was really useful. I hope I left you with something to think about, and that rather than coming away with, I know how to build a complex application, that what you come away with is, I know some patterns that I can apply to attack the problems I have when I try to build a complex application. All right, that does it for my talk. Thank you very much. All right.